The Martian atmosphere is 95% carbon dioxide, a few percent nitrogen, a few percent argon, trace amounts of everything else. But there's still a lot of CO2, and so that's probably the most abundant resource on Mars other than dirt. CO2 has oxygen bound in it, and if we can liberate that oxygen from some of that CO2, then we can use it to do something useful. The goal is to pave the way for future human exploration of Mars by demonstrating the ability to generate oxygen. That's where the magic happens, is inside that box.
NASA is set to launch its next rover to the Red Planet in 2020. Stacked inside are 7 science instruments, 6 of which are focused on sample analysis, like this SuperCam and a spectrometer called Pixel that'll measure chemical signatures inside Martian rocks. And this box getting lowered inside the belly of the rover is MOXIE, or the Mars Oxygen In Situ Resource Utilization Experiment. It's got an agenda separate from the others, and that's to make oxygen on Mars for the first time. Well, at least in real life.
In The Martian, there was something that was called the oxygenator.
If the oxygenator breaks, I'm going to suffocate. If the water reclaimer breaks, I'll die of thirst.
So we jokingly refer to MOXIE as the oxygenator. It's unclear in the movie what technology the oxygenator actually using, but it's very likely that it would be something like MOXIE, but scaled up. MOXIE uses a technology called solid oxide electrolysis. It works a lot like a reverse fuel cell, where instead of putting in a fuel and getting electricity out, we can put electricity in and electrolyze and basically get a fuel and an oxidizer out. On the outside of the rover, we have a small box with a filter. The filter is to make sure that we don't draw in any dust from the Martian atmosphere into our system, because the next thing in the path is a scroll compressor. The scroll compressor takes this low pressure Martian gas from the atmosphere and compresses it and brings it up to something closer to Earth's atmospheric pressure, because the next thing that we do is we run it into this thing. We call this our solid oxide electrolysis stack, and it is basically a layer cake of a bunch of metal plates, which are the dark green things, and then these light colored layers are thin ceramic cells that have particular chemical properties where at high temperature they can conduct electricity using oxygen as the charge carrier. We heat this guy up to about 800 degrees Celsius. You have oxygen ions on one side and you apply a voltage, then you can selectively drive the oxygen through the ceramic membrane and separate it out from whatever's on the other side. It goes through a set of sensors, very much like these sitting here on the table in front of me, and we measure what fraction of CO2 is there. We put CO2 in here, oxygen comes out here, and the waste product, which is a mixture of CO and carbon monoxide and unreacted CO2, comes out here. It's gold because we were concerned that MOXIE itself would run hotter than everything else around it, and we wanted to make sure that we didn't impact any of the nearby electronics boxes inside the rover. And so gold has very low emissivity, which means that it doesn't radiate heat effectively. This particular chemistry process is sort of unique to Mars in its applicability, and also the packaging and how we actually build this system to survive launch and get to Mars. No one has ever done anything like this. MOXIE is going to make about 6 grams per hour of oxygen. It's not very much. It's about enough to keep a small dog alive. We will probably run MOXIE roughly once every 2 months. We don't have the resources available on the rover to run MOXIE for long periods of time continuously, because a lot of the rover energy has to be used for other science that they want to do. The goal for us is to sample different environmental conditions on Mars, so day versus night, summer versus winter, dust storm versus not dust storm, to assess how the technology behaves in response to these changing environmental conditions, because that's what's really useful. What might happen in the future really depends on the technology that NASA decides to go with on Mars. If you only have the CO2 in the atmosphere available, then you'd have something like MOXIE scaled up by about a factor of 200. You'd launch it, deliver it to Mars about 2 years before humans set foot there. It would have a bunch of supporting equipment like a power system and a storage system, and it would sit for 2 years and just generate oxygen and collect it, and then it would be ready for use by the humans when they show up 2 years later. It's really exciting for me to be able to build something that's going to land on another planet. I hope it's going to work the way we expect it to, and that paves the way for future human exploration in the not too distant future. Almost all of my experience prior to coming to JPL and since coming to JPL is in developing hardware, and that has served me very well because you learn a lot of the aspects of how things fit together, what happens at the interfaces. The interfaces are always the most crucial part of a system to make sure things play nice with each other. If you want to build hardware that's going to go to Mars or go to space, you have to know how things get built. Build it and make it work, and that'll serve you very well.